Chapter 17 covers probability models, in particular geometric and binomial probability models. Geometric and binomial probability models are both classified as something called Bernoulli Trials, and these are recognized as such because they meet a certain set of three criteria. So the first of these criteria is that in these trials, there are only two possible outcomes. Okay, and these outcomes are referred to as a success and a failure. Okay, the second criteria is that the probability of success, we use P as the variable to represent that, remains constant throughout these trials. And then the last criteria is that all the trials are independent of one another. Okay, if it meets those three criteria, we're dealing with Bernoulli trials, in which case they could be geometric, they could be binomial, and we have to look at the text of the problem to figure out which one it is. So the first we're looking at is the geometric probability model. And this is telling us, or it's asking us to find the probability of the number of trials until we see the first success. Now, I'm going to hit you with a bunch of information right now, which is going to be a bit confusing until we do the first example. So when we're dealing with a probability model that's geometric, we only have one parameter, which is that probability of success. So based on that probability of success, we're going to get the probability of failure, which we label as Q. And then it's also going to ask us to find the probability of a first success occurring on a certain trial. So for example, what's the probability that we're shooting at a bullseye and we hit the bullseye for the first time on like our fifth shot? Okay, we would use this equation, Q to the x minus 1 power, right, times P. Right, so in this case, 5 would be x. We want to hit it on our fifth shot, so it would be q to the fourth power times p. If we have a 20% chance of hitting the bullseye, we have 80% to the fourth power, which means we missed the first 4 times and then we hit it on the fifth shot. Okay, expected value for a geometric probability model is 1 over p, and then we have a standard deviation given by radical q over p squared. There's also something called an independence condition. It's the 10% condition. This condition comes up over and over again throughout the remaining chapters in the book. Bernoulli trials must be independent. A lot of times they're not. We're going to ignore that as long as we're dealing with a sample that's smaller than 10% of the overall population. So it's okay if they're not independent as long as our sample size is small enough. And by small enough, we mean less than 10% of the overall population. So in this problem, we have a bunch of people standing in line for a blood drive. We know that 6% of people have O negative blood. And the first question it asks is, how many people do we expect to have to examine before we find the first person who has O negative blood? So for a problem like this is geometric because it's a waiting time problem. It's asking how long it'll take until we find that first person who has O negative blood. And the expected value can be found by just 1 over p. P is 0.06. 1 divided by 0.06 gives us 16.67. So that's the average number of people we'd expect to wait or expect to go through before we find one person with that type of blood. What's the probability that the first O negative donor is found in one of the first 4 people in line? So we have to take all the situations into consideration here. So it could be the first person, second person, third, or fourth person. And we want to find probabilities for each of these individually. Okay, so if it's the first person, there's just a 6% chance. For it to be the second person, it means that the first person was not O negative, in which case there was a 94% chance that it was not O negative, and then we found that the second person was. Okay, third person means we had 2 that were not O negative, then the third person was O negative. Okay, fourth person means that we had 3 that were not O negative, fourth person was. Okay, we add all those up, and a total is 0.2193. There's actually a function in our calculator for this. It's called CDF or geometry CDF, depending on which calculator you're in. It's in the distributions. You're going to find it in catalog, which is where you pretty much find everything, but it's also in the distributions tab where we find like normal CDF. Okay, we put in 2 parameters, 0.06 for the probability of success, and we're saying we want it on anywhere in the first 4 trials. Geometric probability models are also known as waiting time problems, where we're waiting until a certain event occurs until we find that specific probability. Related to the last problem, we're waiting until the 4th person in line until we find that O-negative donor, right? Or we're saying how long do we expect to wait until we find an O-negative donor. Compare that to the binomial model, which is where we have a specific number of trials that we're completing, and we want to find a specific number of successes. Okay, so in this model, we're counting a certain number of successes out of a specific number of trials. Okay, they're still Bernoulli trials, so they still have to meet those 3 criteria that we mentioned earlier. So in a binomial model, we have 2 parameters that we're going to define. And when I say that we're defining these, like I said earlier, we define the geometric model with just 1 parameter, the probability of success. I'm talking about kind of like with the normal model, we always note the mean and the standard deviation. So in the binomial model, to define it, we define it with the number of trials and the probability of success. Okay, now also this equation may or may not look familiar. You have seen it before. It's the equation for a combination. It would have come up in Algebra 2, which is telling us how many different ways we can arrange a certain number of objects chosen out of a sample size event. Okay, also this symbol there, that exclamation point, is a factorial. It's telling us to multiply every number from a certain number down to 1. So for example, 4 factorial would be 4 times 3 times 2 times 1. Okay, so in the binomial model, the equation is this. So we're going to do a combination, okay, where we're choosing x items out of n. Then we take the x items that we're choosing and we raise that probability of success to that x power. Okay, and however many items are left over, okay, which is this n minus x here, we raise q to that power. Okay, expected value for a binomial model is just n times p. The variance is npq, and standard deviation is the square root of the variance, square root of npq. So for this problem, we're still dealing with people online for a blood drive, but it's giving us a specific number of people online. So that's a fixed number of trials that it didn't give us in the last problem. And it's saying what's the mean and standard deviation for these 20 people in line, and how many universal donors do we expect among those 20 people, and then what's the probability that there's exactly 2 or 3 universal O-negative donors in those 20 people. Compare that to the last problem where it said, how long do we expect to have to wait before we find our first O-negative donor, or what's the probability that we find our first O-negative donor as the first, as the 4th person in line, or one of the first 4 people in line. Those are waiting time type problems. These are binomial because it's giving us the 20 people, that fixed number of trials. So that being said, we have the same parameters as last time, and we want to find the mean and standard deviation. So for a binomial problem, the mean is just n times p. So in 20 people, we can just multiply that by the probability of success. We expect there to be an average of 1.2 universal donors in this line of 20 people. The standard deviation is radical NPQ, which would give us a standard deviation of 1.062 universal donors in this line. Now, what's the probability that there are 2 or 3 universal donors in this line of 20 people? So we have to do 2 different problems here and then add them together, because that's what or means in statistics. That's this plus sign. So we'll start off with the 2. This is the probability of finding exactly 2 in 20 people. So this first part is finding the combination of 20 choose 2 people. How many different ways can we choose 2 people out of a line of 20 and find them being our 2 universal donors? So in other words, maybe the 2 universal donors are the first 2 people in line. Maybe it's the first person and the 3rd person. Maybe it's the 1st and the 7th, okay, or like the 3rd and the 15th. The point being that there's a lot of different ways that 2 people out of 20 can be the 2 universal donors that we're looking for. And this is telling us how many different ways that can occur. Now, after that, we get a number from that combination, and we're going to multiply it by the probability of a single instance of that occurring. So we have 2 people being universal donors. There's a 6% chance of a single person being a universal donor, and we want 2 of them, so 0.06 to the second power. All other 18 people in the line are not universal donors, so 0.94 to the 18th power. So that gives us our probability of exactly 2. That would be 0.2246. Then we're going to do the same thing for 3 people. 20 choose 3, okay, which means we have 3 people who are universal donors. The other 17 are not. That would be 0.0860. We add them together to get our answer. Now, there's a function in our calculator that we can use, just like there was for geometric models. This one's binomial. It's also in our distributions tab. For this one, we're going to use the one that's PDF instead of CDF. I'm going to explain why in class. But we would have to do this 2 times. We do it once for this one. So if you did this in your calculator, you would see 0.2246. Okay, and that's because we're putting the 2 here. We would change this to a 3 to get this next one. Okay, change this to a 3 and we would see 0.0860 and add them together manually to get our answer. Before moving forward with this slide, I just realized I didn't mention where to find that combinations function in your calculator. It's in the math menu. On the 84, that is 2 buttons below the second key. On the 89, you hit the second key and then hit the 5 button, I believe. Once you're in there, look for PRB for probability and then NCR. All right, moving on. You probably noticed we've been using the normal model more and more in this unit, and that continues as we get further and further into the book. So in order to apply the normal model to a binomial distribution, we need to make sure it meets a key condition, which is called the success-failure condition. And this condition is really just checking to make sure we have enough data to fill out the tails in a bell curve. Okay, so we want to make sure we have at least 10 successes and 10 failures. And to do that, we check to see, does n times p equal a value that's greater than or equal to 10? Same thing with n times q. Okay, if both those values are greater than or equal to 10, we have enough data to fill out the tails in our normal distribution, and we can apply a normal curve to our binomial distribution. Just a note is that a normal curve is really for continuous data, for a continuous random variable. Binomials for discrete. So if we're asked to find the probability of getting exactly 2 people in line out of those 20 people being O-negative donors, we would really want to use a binomial distribution, okay, because that's a discrete question. If it's asking between 2 and 4, it's easier to do that with a normal model. Not necessarily easier. We can do it with either. But discrete problems are harder to do with a normal model. Now in this problem, we have a tennis player who makes successful serves 70% of the time, and she serves 80 times in a match. The question is, does this problem meet the criteria for Bernoulli trials? So I mentioned at the beginning of one of the first slides that there's 3 criteria that we want to check. I'm going to add a 4th here because that creates a easy to remember acronym to help us remember what these criteria are. The acronym is BINS, and the first letter in this acronym is binary. Second is independent, and for number, S for success. So binary means, are there only 2 outcomes? Okay, so in this case, the answer is yes. She's either going to make the serve successfully or she's not going to make the serve successfully. I, independent, are these serves independent of one another? It's telling us in the text of the problem that they are. Now, N is so number, okay, means are there a fixed number of trials? Now, this is the criteria that was not on that original slide, okay, and that's because it's not really a criteria for a Bernoulli trial, it's a criteria for a binomial distribution problem. So if it does not meet this, okay, it could still be a geometric trial. It just can't be a binary distribution, binomial distribution problem. So in this case, there are a fixed number of trials. There's 80 times she's serving in a match. And then S, does the probability of success remain constant? It does, because every time she serves, she has a 70% chance of being successful. So we have these three criteria for our problem. So what's the mean and standard deviation for the number of good serves expected? Do you want to go ahead and pause and attempt? Mean is going to be n times p. 80 times 0.7 would give us a mean of 56 serves. Standard deviation is radical NPQ. Standard deviation 4.099, or moving forward, we'll call that 4.1. Part B, verify that we can use a normal model to approximate the distribution. So here we want to check the success-fail criteria. Make sure that we have enough successes and failures to fill out the edges of that normal model and fill up the tails. So we check NP and NQ. Okay, we see that NP equals 56, NQ equals 24. We write a statement like this, and we have to write that. We can't just write this without the sentence below it. And we expect more than 10 successes and failures, so a normal model can be used. Okay, our normal model would be centered at a mean of 56, that's right in the middle there, and a standard deviation of 4.1. Okay. What's the probability that she makes at least 65 first serves? Why don't you guys go ahead and try this, since you're getting more accomplished at using normal models. Showing the answer now. Well, first off, we would put on 56 in the middle. We're finding the probability of getting 65 or more successful first serves. So we want to find a z-score. Okay, remember, we're always subtracting the mean. So 65 comes first. We subtract that mean of 56, divide by that standard deviation. You get a z-score of 2.195. Now, that's the lower boundary, the lower z-score, and then we're putting in an upper, which would be really anything greater than 3. I always use 99. Okay, and that's going to give us a probability when we go into normal CDF of 0.0141. Okay, so there's a 0.01 or 1.41% chance that she'll get 65 or at least 65 successful first serves.